Okay, so today's speaker is a local speaker, Ozgun Unlu, and he's going to tell us about free group actions on products of two equidimensional spheres. So it's you can
Thank you. So let me start by saying that all through the talk, G is a finite group. Okay, so let me start with actions, with some actions on spheres. So actions on spheres. Now, let's say we have a group homomorphism from G to ON. Then this induces an action, so G action on the n-dimensional Euclidean space. So here, action on V equals Rn. And this action preserves distance, so it induces a G action on the unit sphere inside V. So V is the n-dimensional Euclidean space. So this is the unit sphere in the in Rn. Okay, well, similarly, if we have a group homomorphism from G to UN, then this induces a G action on Cn, and this induces, oh, by the way, this is an n-1 dimensional sphere. Now, if you have a group homomorphism to UN, then you get an action on the n-dimensional complex vector space. So you get a G action on S2n-1. And then similarly, if you have a group homomorphism to the symplectic group, then you get a G action on the n-dimensional, well, H denotes the quaternions here, so you get an action on the n-dimensional vector space over quaternions, and then we have G action on the 4n-1 dimensional sphere. Okay, so this is some way to obtain actions on spheres. Now let me quickly discuss a few examples, some simple examples. Okay, examples. So let's say G is the group, the cyclic group of order 2. So you can send this group to O2 by sending A to 0, 1, 1, 0. Now this induces a G action on S1, sending S1 to S1 by sending XY to YX. So A here, of course, sends S1 to S1. Now, this action has a fixed point. So for example, has a fixed point. Namely the point 1 square root of 2, 1 square root of 2 is fixed by this action. So in this talk, we will usually discuss free actions. So let me quickly remind the definition of a free action. So definition here. Well, an action, a G action on X is called free if for every G in G, and okay, let's say for every X in X, if G is not 1, then G moves X to some other point. Okay, let me give an example of a free action. So let's say G is the cyclic group of order 3. You can send it to U1 by sending B to the third root of unity, and then this gives you a free action. Okay, this G acts freely on S1 using this action. Okay, now a note here is that when you have a free action, when you have an action on V1 and V2, so let's say we have V1 and V2. So by V1 and V2, I mean one of these. Okay, so it could be real, it could be complex, it could be quaternion. Then you get a G action on SV1 plus V2, right? So for example, if G is, again, A squared equals, so here the cyclic group of order 2, then you can send it to O1 by sending A to -1. And this gives the G action on R. Now you can add this to itself. So G action on V plus V plus V, you can add it to itself 3 times and get a free G action on the unit sphere inside this sum. So it will be just S2. So it will be the antipodal action on S2. It will be free. Okay, now, of course, when you change the field, you get more and more complicated actions. So for example, here, let me give example. Okay, so let's say we have Q8 AB such that A to the 4, B to the 4 equals 1, and then the conjugate of A with B is A inverse. Then you can send this to the unitary group, the two-dimensional unitary group, by sending A to the matrix I 0 and 0 minus I, and B to 0 I 0. And this gives a free action of Q8 on S3. So Q8, that's really on S3s. Okay, you could get more and more interesting actions if you use the if you increase the division ring. So for example, you could take the binary icosahedral group. So that is 5RST, and if you send this to SP1, the symplectic group, by sending R to, okay, let me write this a little bit to the left. So R to 1 over 4, square root of 5 minus 1I plus square root of 5 plus 1J plus 2K, and then S to 1 over 2, 1 plus I plus J plus K. And T to 1 over 2, the plus the inverse I plus J, where B is 1 over 2, 1 plus square root of 5. Then the binary icosahedral group acts freely on S3, for example. And as you know, when you quotient out S3 with the binary icosahedral group, you get the Poincare homology sphere. Now, another note that I would like to mention here is if you have a G action on V1 and V2. So last time in the last note, we had actions on V1 and V2, and we put V1 and V2 together first and then apply unitary and then take unit sphere. But another thing you can do is to take the product. So here, okay, okay, now I should say that I'm starting to discuss actions on products of spheres. So here, where M is the dimension of V1 and N is the dimension of V2. Then you get a G action on a product of two equidimensional spheres. So here I added V1 with itself K over M many times and V2 with itself K over N many times. Oh, by the way, K is the least common multiple of M and N, so that the dimensions of the spheres are same. Okay, now some examples of these. So with the actions that we discussed previously, so for example, with the Z3 action on S1, we discussed in this example, sorry, here in this example, we could form a free action on S1 cross S1. Okay, and another example is the hedral group can act freely on two equidimensional spheres. So let's say we have the group generated by ABC, where A squared, B squared, C squared are 1, and then BC is equal to 1, AC is equal to 1, and then BA is equal to BC. Okay, then we could send D8 to U2 by sending A to 0, 1, 1, 0, B to 1, 0, 0, minus 1, and then C to minus 1, 0, 0, minus 1. And then another action that you can obtain is to U1 by sending A to minus 1, and then A to minus 1, sorry, B to minus 1, and C to 1. Then this gives, well, okay, first of all, this part gives a D8 action on S3. This part gives a D8 action on S1, but as in the previous note, we could make the dimensions same because these are coming from linear actions. So D8 acts freely on S3 cross S3, for example. Okay, so here, in this action, C is acting freely, and in this action, A and B are acting freely. So you could see that it will end up having, you will end up having a free action. Okay, now some restrictions. So let's discuss some restrictions. So theorem of Oliver. So Oliver showed that if G acts freely on some Sn cross Sn for some n greater or equal to 1. Okay, so if this, then G cannot contain a copy of A4. So this was one restriction on free actions on Sn cross Sn. Well, there's also a theorem by our colleagues here, Okay and Yalchin. Well, so if G acts freely, so same condition, if G acts freely on Sn cross Sn for some n greater or equal to 1, then G cannot contain a copy of ZP cross ZP, semi-direct SL2P. And then there is a theorem by Connor. Again, if G acts freely on Sn cross Sn for some n, then G cannot contain a copy of ZP cross ZP cross ZP for any prime P. Okay, and then a theorem of Cusick. If G acts freely on S2n cross S2n, okay, this time the dimension is even for some n greater or equal to 1, then G is a subgroup of Z2 cross Z2. Okay, so if the dimensions of the spheres are even, of course, the restriction is very high. I mean, this is not, the idea here was the fact that S2n cross S2n has characteristic equal to 4, and then the point was Z4 is also eliminated by some spectral sequence argument. Here, in these two, the idea was to take the Borel construction of this action and by look at the ideal generated by the n+1 here, and it should be closed under Steenrod operations. So the idea of Connor was again look at the Leray-Serre spectral sequence of the Borel construction, and the Krull dimension should be at most 2. Okay, so
excuse me, what's the assumption on the actions here? Do they need to be smooth or anything?
No, okay, it could be just a CW complex, finite CW complex homotypical equivalent to Sn cross Sn. Doesn't
Okay.
need smoothness here. I mean, none of these terms need smoothness actually. Okay, and then some example by Stein was given that so the symmetric group on 3 letters cross the symmetric group on 3 letters can act freely on Sn cross Sn for some n. Okay, the point is, why is this interesting? Because the symmetric group on 3 letters cannot act on a sphere by itself, but when you take the product, it starts to act. And then in fact, this example was generalized by Hamilton to the case where if G is a product of two groups, and if rank of H1 is less than 1 and rank of H2 is less than 1, then G acts freely on some Sn cross Sn for some n greater or equal to 1. So S3 is a rank 1 group. So here it it's a symmetric group on 3 letters is a rank 1 group. So the examples included in the theorem. Okay, now, well, I want to remind here Milnor symmetry cannot act freely on Sn for any n. Okay, that's why this example is interesting. Okay, now the case when we have a P group. Okay, so I'm going to start discussing the case when G is a P group. Okay, first of all, there is this theorem by Blackburn. So if P is odd, then, and if G doesn't contain a copy of so this was the condition in Conner's theorem, remember, if G does not contain a copy of the P cross set P, then G is in L1 or L2 or L3 or L4. So these are some lists of groups which I will explain. So L1 is all G such that G is a metacyclic group. And then L2 is G such that there exists K greater or equal to 3, such that G is equal to PK. Okay, where PK is the group generated by 3 letters ABC, A to the P, B to the P, C to the P, K minus 2, AC, the commutator of A and C and the commutator of B and C are 1, and then the commutator of A with B is equal to C to the P to the K minus 3. Okay, so these are groups in L2, and then L3 are groups in the following form. So there exists K greater or equal to 3, and there exists epsilon, where this is 1 or a quadratic non-residue. Of P, and the group is equal to some group in this form, BK epsilon. Now, let me also write what BK epsilon is, because I'm going to state some open questions here. So let me be precise about this. C, P to the K minus 2, BC equals 1, AC equals B, and AB equals C to the epsilon P K minus 3. Okay, and L4 is G such that G is a pre-group of maximal class. Okay, now let me state some theorems here. So a theorem of Levis. So if G is an L1, so L1 is the metacyclic ones. G is a metacyclic group. So if G is an L1, then G acts freely on Sn cross Sn for some n. Okay. Here, let me just give a very quick example here. Let's say we have G equals Zp squared semidirect Zp. Now this acts really on S2p minus 1 cross S2p minus 1. The reason is we can take P from G to, okay, let's say these are generated by A and B. Now you can take a non-trivial group homomorphism, so any non-trivial group homomorphism from G over A to U1, and then take, again, a non-trivial group homomorphism from the subgroup A to U1, send A to e to the 2 pi I over 3, and well, the action induced from A to G cross the phi multiplied with itself p many times is equal to S2p minus 1 cross S2p minus 1. Okay. And the action given in this way is free. Okay, and then we have a theorem of Levis again. This says if G is an L2 and G acts freely on Sn cross Sn, then n is equal to 2 pi r minus 1 for some r greater or equal to 1. So here, if G is in one of the groups in the second list, so the list, the groups in this form, then the dimension of the spheres must be this one. And then here we have a theorem, Hamilton. So if G is an L2, then G acts freely on S2p minus 1 cross S2p minus 1. So here the idea was to calculate certain Borgesum groups using the Adams spectral sequence and the James spectral sequence, and then apply surgery on them. But one other method that we used was to do, okay, so the other methods that we used was if G is equal to Z3 cross Z3, semidirect Z3. This is a group in L2, by the way. Here, let's write BC, semidirect A. So here, the commutator of AB is C. Then we can send G to U3. by sending A to 0, 1, 0, 0, 0, 1, and then 1, 0, 0, and then B to 1, 0, 0, 0, W, 0, 0, 0, W squared, and C to W, 0, 0, 0, W, 0, 0, 0, W. And then we can send, let's say, G to U3 again. So we can send A to W, 0, 0, 0, W, 0, 0, 0, W. Here, W is, of course, the third root of unity. So in all these, W denotes the third root of unity. And then B to W, 0, 0, 0, W, 0, 0, 0, 1, and C to just 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, so here the action of C is free, right? So, so we can choose 1, 1, 1 here, no problem. However, the action of B is not free; it has fixed points, and here again it has fixed points. But the idea is that you get some product of two spheres, equidimensional spheres, some S5 cross S5, and there are some fixed points here, and they live inside parts that look like this. So there are parts in this sphere where you have fixed points. Now, what we do is we take out some of these and put them back with free actions and do some kind of dent surgery and obtain free actions on S5 cross S5. So that's another way to prove that these groups in L2 can act. Okay, and then the open problem here for P groups when P is odd is the case when assume P is 3 and G is equal to B for 1. Can G act freely on Sn cross Sn or some n greater or equal to 1? So that's the group that I mentioned in the third list. So we have this group in the third list, and it's the groups in the third list is still an open problem. We could, now, but Blackburn's list was for P groups where P is odd. Okay, now let me discuss the case when P is even. So the rest of the talk is joint work with Chetan. Mustafa say Chetan. So given a rank 2 group G. Now let me remind a few definitions. So definition: a group element of prime order is called a Cauchy element. And then another definition: in a normal series, let's say G1 dot GT equals G, a factor GK over GK minus 1 will be called Cauchy if GK minus 1 owns a Cauchy element. And then another definition is if GK is a normal series, or G star is a normal series, let's say, of G, then rank of G star is the number of Cauchy factors. Okay, then definition by Lawrence and Yelchin. So here, Yelchin. Now the rank of G is the minimum rank of G star. So G star is normal series of G. So the rank defined by Barker and Yelchin is the minimum rank of the Cauchy factors in G. G's the normal series. Okay, and then a theorem by Barker and Yelchin says if the rank of a group is 2, then a G acts freely on Sn cross Sn. Okay, so from now on, we assume the rank of G is greater than 2, because otherwise we have an action. So we have a rank 2 group with rank greater than 2. Now, by a theorem of Maschke, KG is semi-simple. Sorry, let me say QG is semi-simple. So theorem of Martin-Wedderburn. KG is, sorry, let me say QG. QG is equal to a product of matrix algebras where here these are some division algebras. And then theorem of Brouwer-Witt. Every element in the Schur subgroup of the Brouwer group is represented by a cyclotomic algebra Okay, so the components, the components of the Martin-Wedderburn decomposition are in the following form. So they are in the following form: mat n q m, some cross product alpha tau n over h. So in this decomposition, the Division algebras can be written in this form. Sorry, it's not n over h, I should say, where hk is an extremely strong Schroeder pair and then this zeta m is an m root of unity, and n is the normalizer of k. N is the number of elements in the quotient group. Sorry, actually the index, I should say. I don't know if it's normal, just the index. And then m is number of elements in the group h over k. Okay, now here alpha is given by, so the twisting alpha is given by the map from n over h to the automorphisms group of q zeta m, which sends nh to the map that sends zeta m to zeta mi, if n inverse h n k is h I k. Here I'm assuming hk is generated by hk. So hk is a cyclic group. This is a Schroeder pair, so h over k is a cyclic group. So every element in hk is a power of hk, and you take the unique power I and put it over here. Okay, and the twist tau is given by the map that sends nsh nkh, let's say, to zeta mj, where nt inverse ns and k is equal to hj. And here nth is equal to nsh and kh. Okay, here I'm assuming that, say, n over h is equal to n1h, n2h. So I'm fixing some representatives of the cosets and defining this twist according to that representation. So the algebras are in this form. Now, what we do is we multiply this with the real numbers. So
I have a question, a quick question. What is that object in, so this notation, what are the elements as a set of this star product? What are the elements as a set?
It's just, so the elements are, so, okay, let me, let's write this over here. So the elements are NH in H, Q, zeta, M. Okay, and then, then the multiplication is twisted according to, so let me write it like this. Let me give a name, U and H. Now, U and H R product with U and prime H S is equal to this product H and then tau and H and prime H and then alpha R R S. So like, okay, so the multiplication is twisted by these two. Yes.
Okay, I see. So the H subgroups, so there, everything is uniquely determined somehow, right? Because it's a decomposition of the group algebra. So we know we know the subgroups H.
Yes.
That appear in the. Okay.
Right. So it's unique to isomorphism. I mean, this decomposition. Up to, I mean, R is determined, division algebras are determined up to some permutation.
Okay, thank you.
Welcome. Now, if this is a composition algebra, if is a composition algebra, oh, sorry. Sorry, this could separate, of course, sorry. This is a simple algebra. And now this could be decomposed again. So it's like S1, D1 tilde, plus some SK, DS tilde. Now, if some di tilde is a composition algebra, and and SI is, let's say, 2, then since there's this quadratic form on this, we could take average and we can obtain a G action on SD SI. Now, the good thing about this is that you can control the dimensions a little bit. This was some joint work with Yalchin. Methods about quasi-linear actions. Well, using these, we obtain an infinite family of new examples, which is not covered in any of the previous theorems. Now here, okay, I'm out of time, so let me just write down an open problem that we couldn't handle. So let G be a rank 2 group. Rank 2 group. Such that the cell rank of G is greater or equal to 2, and let's say all minimal extremely strong Schroeder pairs H K of G have the following property. So G over the normalizer of K is greater than 2, or the normalizer of this group is equal to 2, and normalizer of K divided by K is a rank 2 group. Then the question is, can G act freely? On Sn cross Sn. So these are groups that we couldn't handle with these methods. Okay, yes. So this is all I want to say. Let me finish with this open problem. But as I said, we have an infinite family of examples using these techniques.
Okay, thank you very much. So are there any questions for the speaker?
Ozgun, what's the composition algebra on the previous page?
So composition algebra are, so it's a algebra with a norm. So I mean, basically it's things like R, C, H, octonions, Sedonians. Sorry, Sedonians is not, octonians is the last one, I think. So some versions of these.
Also, this rational representation theory you're using, are you assuming that G is P group on these?
G is 2 group.
Pairs and,
G is 2 group in all these 4 pages.
So did you look at the Serge Book's rational representation ring? Comes from these simple subquotients. Certain subquotients, his genetic basis he finds for the rational representation ring. These genetic bases looks like these subquotients you're using in the SOTA pairs. Do you know the connection at all? Or?
I'm not sure about the connection. We use Schroeder pairs.
Okay, there's something called genetic bases and subquotients. So every irreducible becomes, or the bases are induced, inflated and induced from these certain subquotients. Does the main idea here is same? Or?
Yes, same idea. That's right.
And you said these are the cases we couldn't handle on the question. What do you mean by, because this looks like bigger than 2 and equals to 2. So which cases you handle, or what do you mean by this?
If this is greater than 2, we cannot handle. So and if this is equal to 2 and this is a rank 2 group, then again, we cannot handle. So HK is the Schroeder pair. I guess the pairs that you were, similar to the pairs you were mentioning.
So do excess special 2 groups fall into those kind of groups that satisfy these properties?
Well, it's rank 2, so
there are not many rank 2 extra specials. Only
yes,
the dihedral.
I mean, there isn't many such things in rank 2. I mean, once you say rank 2, the extra special ones are pretty limited, I guess.
I always wondered.
Okay, that would be too small for that.
There is a paper which is supposed to give a classification of rank to 2 groups. Is that a complete classification? Do you know what is the status on that?
We couldn't make use of it. I mean, yes, we saw some classifications, but I don't know. We couldn't make use of it as like the Blackburn classification. It's somehow different. Seems like a different story here, or maybe we couldn't find any.
You mean classification of P groups?
2 groups.
2 groups.
Rank
Is
2.
it so bad?
It's bad. Yes.
Like, is there infinitely many family? What is the kind of content of it? Like, Blackburn has 4 types, right? Is there a similar?
But Blackburn, P is odd. And
yeah, but P equals 2, is it similar? Like, there's a finite many classes, or there are infinite
there are
many?
finite many classes, I think. Yes.
Okay.
Yes. I don't remember the number of classes there. It was much more than 4.
Is it a Janko paper or another paper?
Yes, yes, that's right, Janko. So, okay, maybe, yeah.
So for these questions, what kind of method? Is it the surgery method you're applying, or the?
Yeah, actually, the thing is, so my hope is that, so there was this this method that I mentioned, where you take out some parts that contain fixed points and replace with free ones. My hope is it will be easier to do such things on these algebras by some deformation theory, maybe. But the deformation theory of composition algebras is not very well developed, so I'm not sure if it will work. But I think the corresponding idea to that dance surgery thing will be the deformations of these algebras with certain algebras, I guess. So I'm not sure.
It's going to be technical, I guess. But before the surgery, you're going to start with something with the induced from the center. So you will assume the center is cyclic, I guess. And then the second representation, you are taking the one that comes from the Shoda pair. Is that the idea, or?
Yeah, I mean, usually you take the minimal Shoda pair, and you like get some algebra that doesn't quite work, but well, okay. The point is, as long as this thing stays as 2, and or maybe okay, even if it becomes 4, maybe. So if this thing is equal to 4, maybe there might be a deformation of the algebra and give the action, which would correspond to surgery, I think. but I'm not sure yet. But it at least gives some infinite family, which is not covered by previous theorems. It still covers a family. It's not everything.
Okay, any other questions? Okay, then, so let's thank the speaker for this nice talk. Thank you very much.